Hello, today I'm very excited to talk about our work on improving the speed of post-breach threat hunting by leveraging novel hierarchical storage design. This is a joint work with University of Illinois Urbana-Champaign, NEC Labs, UT Dallas, Peking University, and University of Central Oklahoma. So modern enterprise security solutions constantly monitor activities on the end host and raise threat alerts if potentially malicious behaviors are observed. To determine the veracity of these alerts, security analysts usually generate contextual and historical information around generated threat alerts. And one way to generate that information is to perform data provenance analysis. Data provenance is a detailed history of system execution in the context of system logs. Using data provenance, we can parse system logs into causal graphs or dependency graphs. In these graphs, vertices represent system subjects and objects such as processes and files, while edges represent causal relationship between system subjects and objects. Each causal graph can have one or more causal paths where each causal path represents one possible flow of information. Such graphs are useful in generating contextual information around given symptom and in this case threat alerts. For example, if there is a threat alert related to a suspicious looking file called mal.exe, we can generate causal graph of this mal.exe file to see how this file ended up in our system. Typically, these graphs are generated as follows. First, when a threat detector generates threat alerts, security analysts send those alerts to a causal tracker to construct causal graphs of given alerts. Causal tracker then derives causal relationships of system events related to the given alert by reading system logs from the disk, and finally present causal graph to the analyst. Now in this case, reading from a disk incurs a significant I/O bottleneck, and performing causal analysis after the fact leads to long delays. Sometimes it even takes hours to respond to each alert query sent by the analyst. At first glance, this time overhead may not seem much for one alert, but in an enterprise setting where thousands of alerts are typically generated per day, these alerts can quickly add up and create a backlog of investigation tasks for the analysts, increasing attackers' dwell time in the victim's network. Studies have shown that the damage wrought by the attacker increases exponentially as the dwell time of attacker increases. In fact, for each day the attacker stays in the network, the organization loses around $32,000 on average. Thus, it is extremely imperative to give security analysts the tools that enables them to quickly complete threat investigation. In order to solve this challenge, we built the Swift system. Swift provides quick and real-time causal graph generation capabilities to security analysts. Swift's key idea is to generate causal graphs in an online fashion and eliminate slow disk accesses during causal graph generation by speculatively keeping the forensically relevant causal graphs in the main memory. Or in other words, the Swift system does not cache benign events in the limited main memory and use the memory for storing only potentially malicious segments of causal graph to enable fast after the fact threat investigation. Now let's see how Swift works. First, enterprise-wide system logs are fetched by our consumer threads using Kafka Broker. Each consumer thread buffers the event for a certain period of time to organize out-of-order events based on their timestamp, and merges repeated events with the same source and destination. This allows Swift to significantly reduce the size of the system events without affecting the correctness of causal analysis. Then these system logs are fed into our hierarchical storage management system. This hierarchical storage automatically moves causal graph segments between main memory and disk to achieve high throughput data ingestion and low latency query results. In this storage system, streaming events first go into tracking cache to derive causality of current system events and generate causal graphs. After that, the Swift system moves causal events from tracking cache to suspicious cache. This cache decides which events are forensically relevant and then store them in main memory. To figure out forensically relevant Swift calculates suspiciousness of each causal path seen in the enterprise, and only stored the most suspicious causal paths in the main memory. Events that are not in the list of most suspicious causal paths are evicted to the disks. Later, when security analyst issues a query to generate contextual history of a given threat alert, our front end will fetch relevant graph segments from the hierarchical storage and present causal graph to the security analyst in real time. In the next few slides, I will explain tracking cache and suspicious cache in much more detail. As I mentioned before, Swift takes the stream of system logs and identifies causal relationship between each new event and past event in order to build a causal graph. The role of the tracking cache is to ensure that the events most relevant to the graph building process are constantly available in the main memory. This enables Swift to ingest gigabytes of system events in a scalable fashion. In order to achieve this goal of scalable ingestion, first we build a novel vertex-centric graph schema and database that is tailored for online causality analysis. This in-memory causal graph database is space efficient and requires minimal disk operations while tracking causality of streaming events. Second, we keep recent system logs for certain epoch in the main memory. This is based on the observation that recent events have a high probability of dependence with the upcoming events in the near future. This allows Swift to eliminate disk reads and write while building causal graph. We validated this observation at NEC Labs and discovered that 98% of the events' immediate dependencies occurred in a 15-minute window. In other words, by storing most recent 15 minutes of the event in the main memory, we effectively eliminated 98% of the disk excesses. Once Swift has constructed the causal graph of streaming system events, Swift moved those graph segments from tracking cache to the suspicious cache. The goal of suspicious cache is to retain forensically relevant causal graph segment in the main memory. To achieve this goal, Swift formulated a hypothesis that states that true attacks are likely to fall on the most suspicious causal paths, and caching such suspicious paths will increase the likelihood that all forensically relevant information will exist in the main memory at the time of the investigation. This hypothesis is already validated by previous projects such as Nodus and Prior Tracker. So based on this hypothesis, Swift devised an eviction algorithm that prioritizes retention of vertices that fall in the top k most suspicious causal paths throughout the history of system execution and evict rest of the causal paths to the disk. In our eviction algorithm, we introduced a time window delta t evict. At the end of this time window, Swift asynchronously runs an eviction algorithm to calculate the most suspicious causal paths and moves the segments of the causal graph that are not contained in the top k most suspicious paths to the disk. Since most of the attack-related causal graphs remain in the main memory at the end of the eviction process, this enables Swift to generate or construct causal graphs quickly by reading most of the data from the main memory. So we evaluated our Swift system at NEC Labs and used their commercially available threat detection software for producing threat alerts. We monitored more than 1 billion system events from 191 hosts. We got around 140 threat alerts over a period of 10 days. In these 140 alerts, we had 128 false alarms, which were validated by the analyst, and we had 12 true alerts that were related to our injected APT attacks. In order to evaluate the effectiveness of our system, we measured the response time of causal graph generation queries for all 140 threat alerts. We chose Nodus as a baseline system that uses only disk storage for causal graph generation. As you can see from the CDF chart that Swift took less than 2 minutes to process all graph generation queries. In comparison, Nodus took more than 1 hour to return the same results. To further investigate the reason for these time reduction, we also studied what was maintained in the main memory and stored on the disk for 10 APT attacks that we simulated at NEC Labs. These attacks are shown on the slide. In this table, the column all events represents all the enterprise-wide system events that were collected at NEC Labs, while The critical events column represent only attack related events. The percentage cached column shows the percentage of the events cached in the main memory. This table shows that Swift had a much lower response time because it effectively cached most of the events that were related to the attacks in the main memory. In other words, Swift was able to significantly reduce disk IOs while generating causal graph for the attacks. To conclude, threat hunting has a huge demand for high throughput and low latency investigation queries. We present Swift system a causality tracker for which scalability and performance are first-class citizens. Swift is capable of identifying in-progress threats and provides quick investigation capabilities. We deployed and evaluated Swift at NEC Labs, and evaluation results shows that Swift can capture all causality information related to true attacks and store them in main memory, which allowed analysts to perform real-time investigations. Thank you so much for listening. I'm happy to take any questions now.